So Andreas, please take it away.
Okay, thank you. Do you hear me?
Yes.
Okay, excellent. So I will give an ESS facility update, and given the fact that we are still a construction site, it will be very different compared to the ILL facility update, which we've been hearing yesterday. So let's start with an old aerial view, which is 2 years old, shortly before the user meeting, the last user meeting, which was in October 2018. And you can see at that stage, there wasn't much to see yet, apart from foundations and the first parts of the monolith of the target, from the target building. And in the upper part of the picture, you can see the large guide hall for the long instruments, which was already there at that stage. Now, this is how it looks right now. So you can see there's a lot of progress. You can see the target building, which is actually nearing completion. You can see around it the instruments hall, the medium and the short, for the medium and short instruments one. And actually, if I look out of my window, this is around 2 weeks old, I can see even more progress. So there's really day by day and week by week, there's significant progress. So there's already more walls have come on and things like that. The building looks really nearly completed from the outside by now. So that's really, really very impressive. And also, well, this is an overall aerial view now, how the facility currently looks. You see in the upper right-hand side, the green part, that's where the accelerator tunnel is with all the gallery, accelerator gallery next to it. And then you see the big target building with the instrument halls. On the left-hand side to that, you see the big instrument hall for the long instruments. And then actually to the lower left-hand side, you can see the new office building and the new lab building, which weren't there at all 2 years ago, which have come up very quickly. And in front of that, on the lower left-hand side, you can see the entrance building and even the parking lot coming up. Overall, in project terms, the overall facility, the construction of the facility, including installation and everything, is by now 70%, 72% complete. Now, let me go into some more details. For example, for the accelerator, if you go into the accelerator tunnel nowadays, much has happened. It's full of equipment, getting more every day. There's 8 kilometers of piping, 14 kilometers of raceway, and more than 120 kilometers of cable already in the accelerator, and more cables are now currently arriving for the superconducting linac. So there's heavy installation work going on and making good progress. Similar for the target, what you see here on the left-hand side, that's actually the target wheel, right? You remember the tungsten target wheel, which will rotate, actively cooled, which is actually the target, the spallation target. In the center, you see the big monolith vessel, which will go into the monolith. It's due to arrive October. It is delayed. I'll talk a little bit more about timescales shortly, but it is due to arrive very shortly now. And on the lower right-hand side, you can, this shaft-like thing, that's actually the shaft onto which the rotating target will be put, and that's which will hold the target and rotate the target. So you can see things are coming together and things will be arriving at site. And what you also see there on the right-hand side, on the upper part, that's part of the bunker, the interface between the instruments, the heavy shielding between the instruments and the target, which will house many instrument components, choppers, and which is also making really good progress. I have some more pictures on that. A more detailed view into the instrument hall. That's DO1. That's the medium for the medium length instruments, right attached to the target building. That's how it looked there just about 2 weeks ago. It's even more closed up now than it looks there. On the left-hand side, you see, that's the interface where the bunker is, where the target monolith is, this roundish thing you see there on the left-hand side. We also, in the meantime, and some of you may have been involved in this, we have the large instrument hall. We took that over quite exactly a year ago, and we had a nice event as part of our ICON meeting, the meeting with our in-kind contributors building these 15 instruments. And actually to document and celebrate that, we actually took this photo where we set ourselves up in the shape of the 15 instruments which we are building. And I have the privilege, together with our DG and our Skanska project manager and our council vice chair, to serve as the target in the center of the building. This actually is an overview of the interior of the long guide hall. That's a little less than a year ago, when installation started, after it had been handed over. What you see in the front up is all the equipment for the labs coming, which are attached to the big hall, where we have various labs being set up and the installation is going on. By now, this hall is much more filled than it was at that time, and you see some photos and an overview here. So, for example, NMX, that's one of the instruments, that the cave for that instrument, you see that on the right-hand side, that is completed already. Another cave by the Bifrost instrument is being constructed right now as we speak and making good progress. And the hutch, that's where actually the operators of the instrument will sit, and from where the instrument will be run for Bifrost has already been finished. Neutron guide interface plates that you can see them on the lower right-hand side have all been installed. And actually what you don't see there, but what is also has happened, there's a lot of shielding. The lower part of the guide shielding has already been also placed in the hall. The electrical infrastructure in that hall, the installation has started. There's a big integration tent, also which you saw in the previous picture, which is for the neutron beam port optical inserts, the inserts which go right into the target, which will be delivered to the first components which need to go in there. And there's also the fit out of the workshops and the labs in the buildings attached to the E1, to the E hall, is also making good program. It had been interrupted due to COVID-19, but it has resumed in July and is happening as we speak. Then again, the bunker, you see that, and on the right-hand side, the proud team, when the first components, the so-called R6 sections, which are directly connected to the target monolith, had been installed. And much more components have been manufactured and are awaiting transport to ESS. You see that on the lower left-hand side, the bunker west wall is already set up in a test assembly here, the pre-assembly, and will soon be transported with a large number of trucks actually to the ESS site. Another thing is, for example, for Bifrost, the vacuum tank that has been built, and it's currently preparing for the factory acceptance test. And you also see the first of the heavy shutters for the test beam line, which is already delivered. So you can see lots of progress is happening and things are moving forward. I showed you that we also have an office building and a lab building, and here are two views into the interior. It's the atrium of the office building, and there's a large, big hall in the lab building, which will be shared by many parts of the organization, like accelerator, choppers, detectors, sample environment, and so on. And of course, as the facility evolved, the way this big space is shared can be adapted to whatever the needs are. We are planning to move both into the office building and the lab building early next year in the first quarter, and we are organizing ourselves to get that done. It's already worked out who will go where, who will sit where, and all these things are already decided. And we are really looking forward to move out of our temporary barracks into this very nice building and the lab building. But of course, you know, we also have a part in Denmark, the Data Management and Software Center in Copenhagen, that also has an important infrastructure. That's the data center, which is, you can imagine it as something of the future cloud of ESS. That was a very professional data center with all the protection you need. And the first phase of the server infrastructure is already installed. And as you can see, there's space for much more as the facility grows and evolves. And what you can see there, that's the opening ceremony with probably the currently world's largest RJ45 network connector, and represent our DG and a representative from the Swedish Research Ministry are working hard to make that connection. We had a lot of fun with this ceremony. Yes, so obviously we all know we are in the midst of a historic pandemic. So I would like to inform you a little bit how that has affected us and how progress is. So first of all, we, like many others, we have been ordered into work from home, whoever can in March 2020. The only exception was those who were actually needed on site for actual installation work were allowed on site. Everybody else had to work from home. The construction company, Skanska, they managed to keep up the progress, keep up working at something like 85 to 90% capacity. So there was a little bit of a slowdown, but not dramatic. And that's why you can see why there is still so good progress on the construction side. And many of our in-kind partners have, of course, been affected by shutdowns and things like that, which, as you may know, there have been no shutdowns of that kind in Sweden, but in many other European countries that has happened. So there have been effect on the work by many in-kind partners, which then in turn also affects the delivery dates for components to used for ESS. So we have a detailed survey of the in-kind supply chain, and that does show a delay of something between 2 and 7 months, depending on what we are talking about, which components we are talking about. So there is a delay, but it's not dramatic, but it's visible, and it will show up in the schedule. Now, since September 1st, we are repopulating the ESS offices to a maximum of 50% occupancy with appropriate social distancing. So, because of course we don't want to continue operating in a 100% work from home mode, because to officially run an organization, it's actually important that you meet your colleagues. But so we found a compromise which actually works quite well, and we have an office occupancy somewhere between 30 and 50% now, and people are quite happy to be partially back to work. Now let me come to the schedule which we have and how it has evolved. There's lots of information on that slide, so I'll try to take you step by step through the slide. So that's at the top, what is shown here, this line where it says BOT, beam on target, FS, first science, SOUP, start of user operation, and EOC, end of construction, these stars. That is the baseline, which we, after our rebaselining a while ago, we were working to, and that did work quite well. But in the meantime, we have experienced delays, and you can see that from these as shown there for accelerator, for target, and for instruments. So the accelerator has been delayed somewhat, but what has always been on the critical path and defined the critical path to beam on target was the completion of the target, and there have been delays of in some about 8 months, which has moved the beam on target to now March 2023. Accelerator has also had some delays, but they are not on the critical path. So the critical path is as before determined by the target building. NSS instruments, they can obviously only start operating instruments as soon as there's beam on target. Installation, construction, manufacturing is making good progress. And there will be something like 6 to 7 instruments ready when we have beam on target. So all of this looks quite good. And then at the bottom area, you see then, so we would have beam on target in March 2023. First science, then 9 months later in November 2023, and start of user operation then in September 24. And I'll talk a little bit more about, especially about first science shortly. Of course, as we all know, the pandemic situation is still dynamic, so we don't know if we will have to deal with additional delays as time continues. This is also why it will take some. So we're doing a rolling wave planning. That's what we call it. We are not doing a full rebaselining yet because we don't know the full external impacts of the corona pandemic because it is still evolving. This is why we will do a full rebaselining probably only in the second half of next year when we have a full overview of any potential delays due to corona. Okay, let me talk about the instrument suite, because that's probably what this audience is most interested in. As you know, we have 15 instruments under construction, and they are all in-kind contribution, and that's represented by the country flags from all the in-kind partners building the various instruments. You probably know all this. As I said, the current NSS schedule foresees that we will have 6, maybe 7 instruments at least ready for beam on target, and in the list below there should these first 8 instruments that, which is the first wave of instruments we are planning. These are shown in bold there, and you know that they cover various techniques. And of those first 8, quite a while ago we selected the first 3, which are the ones which we will focus most on, where we also have the highest hope to actually get first science out of them. And these are Loki, a science machine, DREAM, a powder diffractometer, and Odin, an imaging machine. And manufacturing-wise and so on, schedule-wise, it all looks good. So there have been no changes here. So we are quite happy about that. Yeah, very important. We did, together with our in-kind partners, write a big instrument paper, which has appeared last year, early this year actually, in nuclear instruments and methods in physics research. So if you want any, so this is the reference for the next years on all the overview of the instruments, and also on design of the moderator and the history and how it led to the current instrumentation suite, which we are currently building. So this is a good reference, and there will be, based on this, a wave of more detailed individual instruments paper, which will follow that somewhat later. Good. Now this is the instrument 15, 1 to 15, which we are currently building, and they are all funded from the construction budget. And those who participated in the last user meeting may remember that at that stage we had just published a capability gap analysis for the remaining instruments 16 to 22, which we are supposed to build at ESS as soon as we can, and as soon as we have the funding for that. So we started this whole process in coming up with this capability gap analysis to discuss with you, the user community, what your input on this is, and then subsequently we continue the discussion within the ESS governance. So just to remind you what we told you, presented to you last time, we had 3 priority gaps, the highest, a medium one, and a lower priority capability gaps. And there's a detailed document and paper. The link where you can download it is shown on the lower left-hand side, where we argue why we think this should be the priority, and how in continuing with those instruments. So the highest priority would be a fundamental/particle physics beamline. There's a very good proposal for an ANI beamline, which was only not approved within the first 15 because there was simply not enough funding at that stage to fund another beamline, but it was very good. The same was, the general agreement, really need a high resolution spin echo machine. That's obviously something which we are missing. And that's another high priority. At that time, the details of the proposals were not quite there yet, that it could be supported, and also there was not enough funding for a 16th machine. But we think that this is the highest priority. And then there are many other proposals and ideas. Many are proposals which couldn't be funded within the first 15, but which of course are still there and can be updated. And there are also some new ideas. And of course, there's still room for new ideas. So we have discussed it at the last user meeting. We have then discussed it in detail with our scientific advisory committee, and our SAC fully supports the highest priority for those 2 instruments. And for the others, we all agree, and that was also our proposal from the time, we would then an open call for the other instruments and look at that and do a similar selection and prioritization scheme as we've done for instruments 1 to 15. And the recommendation then was also that we should tension building new instruments against, improving, completing, upgrading, whatever you want to name it, the existing instruments, which you may remember are not built with a full scope, but they all have a day one scope. So there's room for improvement also for those instruments. And as part of those, this upcoming call for proposals, of course, also new ideas will be welcome. So that's quite, and just to show you here, so for the first two priorities, these are 6 instruments. This is how they could be placed. Obviously, that's an important boundary condition that they fit into the existing instrument hall. And that's also part we don't have any space for the really long instruments. The long instrument hall is already filled. But these instruments would all fit into the existing building, so there's no further cost incurred on that side. Now, where are we with this whole thing? So as I said, we presented it 2 years ago to you. After that, we discussed it in detail with the Scientific Advisory Committee last year. And I already told you last time that the whole progress depends on agreement to the initial operations budget of ESS. That's at least the budget we need until 2025 to get this started. And we'll probably need to use budget well beyond 2025 to fund all of these 6 instruments. Fact is, there has been progress made, but there's still no final agreement on the full budget up to 2025. Actually, in the whole process, it has also turned out that our member countries will only be able to provide somewhat less initial operations budget than initially planned. It's probably about 10% less than they originally were hoping to be able to provide. So that, of course, also doesn't help in moving this process forward. But on the other hand, as I'm sure you will all agree, there are very long lead times until there will be an instrument. It's 1 to 2 years for the call for proposals and a decision process, and then another 6 years for design, procurement, manufacture, installation, and commissioning of an instrument. So that's 7 to 8 years until we would have further instrument actually in operation. So that would be by 2027 or 2028 then. And obviously that means we should start as soon as possible, but obviously we need agreement from our member countries to go forward because obviously the funding side also needs to be clarified. And we will hope, I do hope that maybe we can start the process next year. Another important topic is first science. So first science is this milestone you've seen about 9 months after beam on target. So what is first science? How do we define that? Well, first of all, once we have hot commissioned the instrument to make sure that they can be safely operated, you need to test them and use, for example, samples which have been measured elsewhere at other facilities to make sure we can reproduce data. So just to make sure those instruments work properly, and you can also see how they perform in comparison to other instruments. All of this will obviously happen at very low power because only shortly after beam on target. So by that time, we will only have something of maybe 100 or 200 kilowatt or so on the spallation source. Once that's done, then we can start to do first science experiments. So once we know we can trust the data which comes out of the instrument, we do first science experiments. And this definition has come out with a very productive discussion with our Scientific Advisory Council. All of this will take place during hot commission of the instrument and the source. So things will not work properly. It will be debugging at the same time. It will be a very exciting, stressful time. We need a working neutron source, but it's clear that the availability can still be low because the neutron source will also be commissioned at that time. And to manage to get a real experiment done, even if it's scientifically simple, will be a major achievement. So it will be an interesting, tough time. But it will be the first output we were aiming for, obviously, at ESS. Only then, at some stage later, roughly another 9 months later, we will then aim for the start of user operation when the instruments are and the source have an acceptable reliability, and we can be sure that everything is sufficiently well understood, so that users which come actually go home with data and without any major failures. So that's the overall plan. So how do we plan to achieve this? We consider all the instruments for first science which were in hot commissioning, but of course we do focus on the first three, Loki, Odin, and Dream. But we will also ensure that the others which are ready for hot commissioning also have plans in place, because there might be changes because something doesn't work as it should be, so we have others who can jump in. All instrument scientists are asked to develop ideas and collaborations, also outside collaborations. Cross collaboration between instrument scientists is of course encouraged and managed internally. We have our instrument class coordinators who help develop ideas and link teams within other parts of ESS, like sample environment data management and so on. We have an external, the so-called scientific and technical advisory panels, STUPs, which give advice on those plans. We have STUPs for each instrument class, like diffractometers, small angle, large scale structures, and so on. That's already underway, detailed discussions on first science. And we also plan to exclude external experts. You can call them friendly users, although somebody told me there are no friendly users. I think we will find some via a transparent process in first science. And all of this is being discussed with SAC and will be further developed with our scientific advisory body and with our governance. Good. So I come to conclusions. So I hope I have shown you that we are making good progress. We do have some impact by the ongoing pandemic. Installation of instrument and the scientific infrastructure is progressing well, and we plan beam on target and first science in 2023. And now I'm happy to take questions. Thank you for your attention.
Thank you, Andreas. Thank you for a very nice summary and for keeping to time. We actually have several questions have come through, so let me ask a few of them. The first one comes back to the question on first science, Andreas. The question is, what would be the source parameters, the power and the source characteristics at that point of first science?
Yes, very good question. So we have a detailed planning and an agreement with the technical directorate what that could be, and we think it could be something on the order of maybe 100 or 200 kilowatts. But maybe even if for whatever reason it's only 50 kilowatts, it will be already a good amount of neutrons to be using. It will be on the order of what other existing spallation sources provide. And actually, we've also already looked at the performance, which our instruments, if they work properly, of course, would provide at such something like 200 kilowatt spallation power. And you see that at that time, they would already be quite comparative to other good machines in Europe and elsewhere. So in principle, this should already be very interesting times to get first science out of these instruments.
Thank you, Andreas. Let me move on. I think I've got time for maybe one or two more questions. The next one is about the instruments 16 to 22. There's a few questions about that, Andreas. One is, do you foresee something like an open call, or how would people feed in their ideas for what these instruments might be?
Yes, it will be an open call. Many of you may remember how we did this for the instruments 1 to 15, and it will be similar to that. I mean, I mentioned that we have these highest, the first category where we actually say, well, yes, we want a fundamental particle physics beamline and a high resolution machine. Obviously, it will be an open call for these types of machines, but obviously what we assume and expect and hope is that those partners who in earlier times have written proposals which have already been looked at in great detail would update their proposals and submit those. So for the highest priority gap for those two instruments, it would be only open that it's focused on these two instruments where there seems to be wide agreement that that's really what we need first. For the others, then the category 2 and 3, we would make it an open call. And of course, we would assume that very good proposals which are on that list will be resubmitted in an updated fashion, but at the same time, there's complete openness to any other new idea. And we are hoping, of course, to great new ideas which can make help ESS make a success.
Thank you, Andreas. We're actually we're out of time, but there's a lot of questions flooding in. So let me just ask you one more. And I guess the question is about what could happen beyond 22. So the question is, could we see perhaps through a CRG type scheme, could we see further expansion?
Okay, excellent question. So first of all, yes, we can. We have room for more instruments. So the formal scope of ESS is to build 22 instruments, but obviously the way the facility was planned and designed, there is room for additional instrument halls, upgrade space, which would allow for something like up to 35 beamlines or so. And we have nice graphs which show you how this would look. I just don't have them in this presentation here. And how we then go about financing these additional instruments, if this is a CRG model or something like we are doing it currently, further public ESS operated instruments provided in kind or however, that hasn't been discussed and decided in our governance. But I think probably it will be evolving in a way which is somewhat similar to what we've seen at other facilities. So I could imagine that in the later life of the facility, there would be room for CRG type instruments.
Okay, thank you, Andreas. There are more questions, but we're out of time, so we'll try to pick up those by a response offline. So thank you, Andreas. If you could please stop sharing, I'll introduce the next speaker.
Yeah, I'll try to do that.
So I would say here that we have a link between these two talks. We go from the disorder of the ESS facility construction to correlated disorders, and the speaker is Andrew Goodwin from Oxford University. So welcome, Andrew, and please take over, share the screen.
Well, thank you very much. I don't know, just get that working.
Yes, we can see it.
Working? Yeah. You can see that. Just ask very quick, my cursor.
Yes, we can see the arrow.
Great. Okay, perfect. Thank you very much. As Shane said, for those who don't know me, I'm Andrew Goodwin. I'm a materials chemist here at Oxford. And Chris was just saying there may not be anything as a friendly user. I'm certainly a user of neutron facility. Try to be friendly, but do my best. I'm going to talk today about this idea of correlated disorder. We're really interested in the interplay between this and function in materials. And I've tried to keep the talk today relatively general. I'm going to focus on the use of scattering techniques to characterize correlated disorder, and obviously with emphasis on the use of neutrons. But I'm aware it's quite a broad audience in its own way. So I thought I'd begin just with a couple of examples of chemical systems that show correlated disorder. Let me change this on my screen. So, so this is one. This is a group of materials known as benzene trissamides. Industrially, these are used as nucleating agents for plastic. So they effectively control whether a plastic ends up being transparent or opaque. There's these small planar molecules that you see here, and in the solid state, they stack on top of one another to form these columns. And around the edge of the columns, what you have are directional hydrogen bonds that lend a polarization to each one of these columns. So they have a positive end and a negative end. And as they aggregate to form their own crystals, those columns pack as if on a triangular lattice in the same way that sort of hard spaghetti would pack. But of course, because each individual strand has its own dipole, neighboring strands try and point in opposite directions. And this ends up giving rise to a complex state. I'll show you a picture of what this looks like in just a moment. But what's important here is this mixture of up and down, the domain size of these of particular polarizations actually affect their ability to nucleate those plastic crystals. Here's a chemically very distinct but conceptually related system. This is a metal organic framework known as terbium formate. In the center here, what you have are columns of terbium-centered polyhedra, and those columns are connected to one another via these formate organic linkers. The disorder in this system is not structural, but rather magnetic. The interactions between terbium centers along these columns are ferromagnetic. The spins effectively point in one big collective direction that turns out to be either up or down the column. But of course, as you might have guessed, the interactions from one column to the neighbor are anti-ferromagnetic, and this gives rise to this same sort of geometric frustration we saw in those trisimide crystals. And again, the sort of states you access are conceptually related. In this case, this is a material that has some very good magnetocaloric behavior, and the behavior of this particular system is key to that. This is what hello. Can you hear me?
Hello, Andrew. Yes, we can hear you now. I guess we lost something.
Where did you get to?
I think you were showing a slide of disorder in antiferromagnetic system.
Great. I'm sorry. We have really bad internet here. It's not a good departmental advertisement, is it? There we are. So, had you seen this picture?
It's a checkerboard.
Yeah,
black and white.
That's right. Okay, great. And I
had start there.
Okay, yeah. Okay. So I was just explaining this is the kind of disordered state we might look at. This is what the diffraction pattern might look like for one of those, where you have Bragg component from the underlying lattice. And this.
Sorry, Andrew.
Yeah?
We can't see your shared screen at the moment.
Let me try. I'm sorry. How's that?
Okay. Yeah.
Is that better?
Yeah. So I think you're looking for slide 4, probably.
Have you seen
go back one.
Go back one. There we are.
I think if you start there, that's probably a good place.
Okay. I'm very sorry about that. Our internet's been cutting in and out all day.
Okay.
So how frustrating? Well, in a disordered talk, it might as well be disordered. So there we are. This is one of those disordered states we were just talking about, neither random nor ordered. The diffraction pattern for these sorts of systems looks something like this, where you have a Bragg component from the underlying periodicity of the triangular lattice and a diffuse component that captures information about that disordered state. And of course, as you know, the sort of rule of thumb with diffuse is if you have diffuse scattering in the diffraction pattern, you've got disorder. And if that diffuse scattering is beautiful, then the chances are the origin of that disorder is also beautiful. Here's something I like very much, that in quite different chemical systems showing the same type of disorder, you end up with diffraction patterns that are related one to the other. And that sounds kind of obvious, but it's of course the same sort of idea we use in conventional crystallography. This one that I showed you on the left, the component that has that sort of Ising-like triangular antiferromagnet state is actually a protein. This is a work of Richard Wellebury. In the middle is that trisimide nucleating agent that I showed you, and on the right-hand side is the magnetic neutron scattering from that terbium formate, what you see is this same characteristic honeycomb-like diffuse scattering in each case. In the case of the terbium formate, we're just looking at the powder average. So this signature that you see here with the nuclear Bragg peaks missing is really just the orientational average over what you have in the middle. And of course, diffuse scattering's long been known about. Here's an example from the neutron community, a paper that I'm sure is dear to many people listening in. It's the work of Schull and Smart on antiferromagnetic ordering in MNO. So this is kind of the canonical antiferromagnet. This peak here effectively won a Nobel Prize, basically, showing the existence of antiferromagnetic order. MNO undergoes this transition about 120 Kelvin, but even at temperatures above that, when it's nominally paramagnetic, you still see broad diffuse scattering in that same position. And in fact, here is some data from Matthias Gutmann, now single crystal data. These broad blobs that you see are just this smear that you see in the powder diffraction pattern. And this is characteristic, really, of the existence of non-trivial magnetic structure in paramagnetic MNO. So that's what I mean by sort of correlated disorder and the fact that it has some signature in scattering patterns. Let me just turn quickly to how you might go about analyzing it. There's lots of different ways of doing that. I thought I'd just use MNO as a very simple introductory case for this. So just to remind you of the underlying physics, of course, MNO is a rock salt monoxide. So the manganese sublattice is the FCC lattice that you see here. Dominant magnetic interactions are nearest neighbor antiferromagnetism and next nearest neighbor antiferromagnetism, J1, J2. It's only the first of these that is frustrated because you've got these triangles that you see here. And the strength of these two interactions you can measure using, say, neutron inelastic scattering measurements. They turn out to be relatively similar in strength. You can use those two J values that you have to calculate what you would expect using, say, a Monte Carlo simulation, the kind of magnetic structure within the paramagnetic regime. And once you have that, you can work out what the scattering looks like. And here's a comparison from nearly 20 years ago between a Monte Carlo simulation and a cut through that three-dimensional diffuse scattering that I showed you before. And so that's really quite nice. But of course, this is starting from the theory and comparing with experiment. Very often as experimentalists, we want to take our experiment and derive, say, the structure from that. You can do that in a number of different ways. Here's one that we often use within the group. This is based on the reverse Monte Carlo approach developed by Robert McGreevy, who'll be known to all. Basically, you build a sort of supercell of your underlying structure, decorate it with lots of spins, and then you can calculate from this the scattering, be it either in powder form or in single crystal form. And then simply by moving the spins, you can try and fit those as well as you possibly can. The equations that do this have been in the literature for quite some time. This is a kind of progress that you might get with a powder fit, for example. You start with something that looks like the magnetic form factor and fit eventually. But of course, because you have a sort of single crystal in your computer, you can actually also calculate the single crystal diffuse scattering. So this is often a way of recovering single crystal data from powder, but you can also fit to single crystal data independently. So for example, with MNO, you can do that. Here are Matthias's data. You can do a fit to the whole volume now of scattering data. And that gives you a model. The difference looks pretty good that you can interrogate and learn something now about the magnetic structure. So for example, in this case, you can plot a spin correlation function. You can see that nearest neighbors and then next nearest neighbors are antiferromagnetically coupled. And you can look at sort of more complicated orientational dependent spin correlation functions. This is the one I like. You can take your box and you can start to look for the extent of local ordering. And really the question you might be trying to answer here is, if you're in a paramagnetic state, at some sort of temperature above the Néel temperature, is it the case that the magnetic order that persists, this local order, is it uniform, or is it the case that you have regions that are more strongly ordered than others? And if so, what are the sorts of sizes of those regions? So we can use these kind of sort of local order parameters to probe that kind of local order. And indeed, you find that there are these domains that, depending on exactly where you define a domain beginning, they're usually about sort of 20 angstroms across, where you have quite strong antiferromagnetic order within those and a more disordered region in between, a matrix between, and you can interrogate all that. Okay, so more broadly speaking, what this is suggesting is that if you've got systems with some sort of correlated disorder, that you can use scattering techniques to try and probe what's going on. And just to give you an overview from the materials chemistry community, there are lots of different really important materials where correlated disorder plays a role. And obviously, I'm not going to get a chance to talk about all of these, but an obvious question to ask is, for these disordered systems, to what extent might you hope to really genuinely sort of solve a structure by taking, say, neutron scattering data or X-ray scattering data and inverting that? And I wanted to talk about that inversion problem very quickly, because this becomes really quite problematic. In any scattering experiment, really what we're sensitive to are pair correlations. And the question becomes, if we know the pair correlations in a material, even if it's disordered, can we work out the structure? And it's very easy to show that for certain systems this can't be the case. So a very simple model here would be if I've got 4 objects arranged at the corners of a square, and I calculate the distances. Here are my pair correlations, 4 at unit length and 2 at root 2. I can construct a different arrangement of those 4 objects, so like an equilateral triangle with one above, that has exactly the same set of distances. So in this case, if I couldn't resolve orientation, I'd have no way of distinguishing between these 2 objects. And this, of course, becomes pathological in the case of, say, amorphous materials, where we only have isotropic scattering data. Here's 2 models for amorphous silicon that have exactly the same pair distribution functions, but very different structures and very different higher order correlation functions. But even single crystals are not immune to this. A very obvious example is the case of 2 enantiomers of a single crystal have exactly the same set of 3-dimensional pair correlations. And of course, this comes down to the fact that the Patterson function, and indeed the scattering pattern itself, has inversion symmetry. There are sneakier examples. This is one that Linus Pauling identified in the space group IA3 bar, where if you have an atom on this particular special position and you invert its position in this sort of X component, you end up with 2 different structures that have identical diffraction patterns. And of course, these are examples of what Patterson called homometric structures. So basically, if all we access are pair correlations, even in the case of single crystals, but certainly in the case of disordered materials, we can't necessarily always hope to determine their structures. And this is, of course, one of the things to have in mind when looking for correlated disorder. I just wanted to give you a sense for how we're approaching that problem, this kind of uniqueness problem, and I think what's informing a lot of the way the community operates here. And effectively, we're just using a sort of Bayesian way of thinking about things. We measure some data and we need to infer a model, and we want one model to be much more sort of likely than any other model. And Bayes tells us how to think about that problem. It's not just a matter of finding a model that fits to data, but also taking into account, of course, the quality of the data itself, but also the likelihood, the physical likelihood of a given model. And what you tend to find is that this world of correlated disorder sorts itself out best in 2 cases. One where your data are very sensitive, they can discriminate between different models, this sounds obvious, but the other is where you might have some good understanding of the likelihood of different models. And that really informs, I think, the way people are approaching it. Just to take the second of those aspects first, what do we mean by biasing by model likelihood? Well, it could be obvious things like using empirical potentials to constrain distances and angles within a structure. It could be empirical likelihoods for systems like proteins, where you have good understanding of what structures are found and what aren't. Increasingly, I think we're seeing dovetailing with ab initio techniques that allow us to compare the sort of energies of 2 competing models. And of course, there's the things we've always done as humans, which is to look at our answer and ask, is it actually sensible or not? The other side, this one of collecting data that are as sensitive or discriminating as possible, its own approaches. One is to combine lots of different techniques, say, so combining other things to discriminate between different models. And the other, I'm just getting another warning about my internet, sorry. And the other is to really collect really high quality, very complex diffraction patterns like the sort of 3-dimensional diffuse scattering you see here. And that's the kind of thing that we're focusing on increasingly in our own group. There are lots of different ways of interpreting those sorts of complex scattering patterns, ranging all the way from just theory, perhaps with no variables at all the way through to sort of physics agnostic models like reverse Monte Carlo. I won't go through all of those, of course, just to flag that there's no unique answer, I don't think here, that different systems will be best approached in different sorts of ways, and that the advantages of one are often the disadvantages in other scenarios. Here are just 2 extremes, just to give you 2 examples before I move to my final set of slides. This family, these disordered rock salts, which are actually closely related to what you might see in, say, some cathode materials. You have an ordered FCC sublattice of sulfur, and then a bunch of vacancies and different cations on the other sublattice. Here, magnesium, ytterbium, and vacancies. And if you make the chemically sensible assumption that around each sulfur, the mixture of species on the other sublattice reflect the overall composition, you can actually take that constraint and write it down in this mathematical expression here that traces a surface in reciprocal space that is actually related to where the diffuse scattering ends up. So here's an example of understanding the diffuse scattering in terms of something that has absolutely no parameters, just some chemical intuition. At the other extreme, here's some work that came out of Igor Levin's group looking at these PMN relaxers. These are perovskite-based materials with huge amounts of chemical and physical complexity. In order to assess these systems, what Igor did was together neutron, X-ray, single crystal powder, XAFs, some calculations as well, to produce atomistic models that try and capture what's going on. They were looking for these polar nanoregions. So it's a really complex material that has taken that alternative approach of having lots of different techniques. I would say that there are two recent advances that are particularly relevant to people working in my sort of field. This is in terms of kind of data analysis. One is the development of fast Fourier transform methods for calculating diffuse scattering patterns from large models. And this has been driven by Joe Patterson at Oak Ridge. And because you can now calculate these so quickly, this really allows for very effective fitting of data from a facilities perspective. Is going to mean, you know, big demands on the quality of data that we can measure. And the other is a technique known as three-dimensional difference pair distribution function techniques. In one form or another, these have been around for a little while, but they've really been driven by Thomas Weber and Arkady Simonov, both at the ETH in Zurich. And the idea here is that you take these complex single crystal diffuse scattering patterns and actually analyze them in real space by looking at their Fourier transform. And if you just transform the diffuse scattering and not the Bragg component, you end up with something that is a three-dimensional pair distribution function where you look at the difference from the average structure. Now, I'm mindful of time, so I will try and go through these slides quite quickly. Let me just flag why I think these are so interesting and useful for us as chemists, because what this difference pair distribution function does is allow us very easily to see the microscopic origin for the diffuse scattering that we observe experimentally. We get different signatures in these difference functions if, say, the key thing is compositional, local compositional ordering, or if it's due to correlations and displacements. And if I had a bit more time, I'd go through this, but it's basically if you get a feature that looks a bit like a sort of monopole, or it looks like a quadrupole here, you can distinguish one from the other. And that's because of these differences between the average and the local pair correlations. Here are two nice results from other groups using these approaches, just to show you what these look like. It's a recent result really coming out of Ray Osborne and his collaborators. This is a sodium intercalation compound, vanadium and oxygen. And these spots that you see here, plus or minus and so on, these are telling us that certain pairs between these sodium sites are either occupied more frequently or less frequently than you would expect from the average structure. And this tells us about the arrangement of the sodium ions in the intercalate. And likewise, on the right-hand side, this well-known thermoelectric material, lead telluride, in its three-dimensional difference pair distribution function. You get these features where you've got a sort of red bit with blue bits on either side, and that's this sort of signature that you have here, positive with negative on either side. This is telling us about the correlated displacements, and in this case, really anharmonic phonons that are populated in lead telluride. A nice extension, particularly relevant to the neutron community, to the magnetic difference pair distribution function developed by Nikolai Roth, who's a PhD student in Bo Iverson's group at Aarhus. And this, of course, is capturing a three-dimensional local magnetic structure, such as in the XBI materials. In our own group, we've been looking, for example, at these Prussian blue analogues. This is a problem of vacancy relations. These materials are used in all sorts of areas. Very often, one of the key features is the nature of the pore networks that run through them. And here we're using these diffuse scattering patterns and their three-dimensional difference pair distribution functions to infer information about the arrangement of these vacancies to the other. And just to finish, the really nice thing from our chemical perspective is that what we're finding is by tuning the chemistry of these materials, we navigate meaningfully different disordered phases. And this is really our long-term goal, to work out how do we control the type of disorder within functional materials where we're optimizing the properties by manipulating the disorder that exists within them. And that's the kind of sort of take-home message we got from these sorts of systems. So just to finish this idea of correlated disorder, as a kind of disrupted and hopefully and sort of whistle-stop tour through some of the problems we'd be looking at, where the field is going, I think very much is along that sort of single crystal line, but also say operando measurements for battery materials, interplay between statics and dynamics in systems like thermoelectrics, obviously role of magnetic fields or electric fields in a variety of different functional materials. But hopefully that's given you some flavor for the sorts of things that people like me and others are looking at the moment. And let me just finish by thanking, this is now an old picture of our group. We're not allowed, this would be violating all sorts of rules, obviously, so it's not us at the moment, but our group, our collaborators, and of course the funders in particular, while I can, the European Research Council for funding. I'll finish there.
Thank you, Andrew. Thank you for that talk. I think you did very well considering that brief interruption to get to the material. There are some questions here. I'm not sure that I'm qualified to ask them all, but let me start anyway. The first question, I guess, it relates to the types of systems that you apply this methodology to. And I wonder if you have any examples in the field of quasi-crystal studies.
I don't personally, but the ETH group, obviously Walter Steuer, Thomas Weber, have applied those three-dimensional difference pair distribution functions to quasi-crystalline materials. And I'm not expert in the interpretation there at all, but obviously there's a common flavor of these systems that don't conventional crystallographic rules. I would say that actually these correlated disordered states turn up rather more frequently than quasi-crystalline phases, relevant to lots of different systems that have been for quite some time. So the key thing is, yes, you can use the same techniques, much of it maps. I'm not expert, but I think there's some very common flavors between the two worlds.
Right. Let me go to a question of my own, and then I think we have a moment to ask some others. I'm prompted by seeing that you're talking about magnetocalorics and ferroelectrics and so forth, where we have a stimulus and we have a response that very often has I guess would produce a change. Are there studies, in operando studies done in this field to look directly at the response to the stimulus? There
are. I'd say, just off the top of my head, the world where that's been done most is certainly in the case of frustrated magnetism, where the application of magnetic fields as a perturbation to watch what happens to a frustrated magnetic state in response to that field, has been studied by many groups. I would say that this is one of the really nice aspects of these correlated disordered states, is that because you have this configurational degeneracy, they very often end up being highly perturbable. They're very, very susceptible to external fields. And I think it's absolutely no accident that good magnetocalorics or good barocalorics, for example, are often built on these same principles of geometric frustration and correlated disorder.
Right. Okay. So let me go to another question that's been asked, and I'll just read it. Is there any knowledge about how correlated disorder is formed thermodynamically in various materials, and can we use the relevant knowledge to avoid such disorder formation?
So I would say my goal would be to stop the negativity of the second half of that question. So we would be looking at, when do you actually want correlated disorder and how do you encourage it? But of course there may be cases, it is fair that we grow up thinking about functional materials as being ordered. So the statistical mechanics of many of these systems, including the one on the screen here at the moment, is well established, and these are thermodynamically accessible phases, for given model systems. Obviously, very often you have longer range interactions that will break these in real materials, and the ground states, if you go to the very lowest temperatures, would in fact very often be ordered. For many of the systems that I'm showing, there may also be kinetic trapping, but there's no universal sort of way of saying, oh, I'm going to favor one or the other across chemically very different sorts of systems. I would say that the key thing here is to use the statistical mechanics that's already been sort of developed for these to know what kinds of interactions might favor particular states. And, this would come back to things like looking at these. If I'm going to stack polar objects on a triangular lattice, well, I sort of know where I'm going to end up in terms of the structures. So the flip side works. If you want to get rid of it, then well, why don't I stack this on a square lattice, which isn't frustrated, and then you'll get your crystal if you so want it.
Right. Okay. Thank you. Let me try one more question, and then I think we finish. And I think it's in the nature of the fact that you have to combine many experimental methods, right, to build your picture. And the question is, are you able to formulate results from the different measurement techniques as a way to help you to combine data sets?
So the rigorous combination of data sets is not something that I have, that I don't think the field uses in the way, I guess, eventually we might hope to. So for example, I showed you, I don't know if I'll be able to get to it very quickly, but this sort of tour de force from Igor Levin, where he had a whole variety of different measurements pulled together. Yeah. So here the protocol used was the RMC profile software that people like Matt Tucker have developed. And this has an internal way of pulling together these different measurements, but you do have to play with the weightings of one versus another. Now, I would argue that actually Bayes' theorem gives us a way of naturally weighting these if we have good uncertainties of one measurement relative to the other. But this gets very difficult when you're doing this, but it might be something as a field we have to think a lot more about, because I'm sure Igor would be the first to say that, you do have to spend quite a lot of time working out exactly what weighting you're going to use one relative to the other in order to get the best collective fits that you can obtain.
Okay. Look, I said I'd finish here, but there is one more question. It's actually come in from one of the listeners, and it's interesting to me. And I guess it's about where are the measurements holding you up? Where are the limitations? And is there something that you would say would be really useful in terms of improvements in instrumentation, in the quality of the data you can obtain?
Well, that's an extremely good question. As I'm sure whoever's asked it has in mind, often our limitation is actually just data analysis, that this is, takes a long time from one of these data sets. But it is clear that the quality, particularly say in the case of single crystal diffuse scattering, the quality of the data sets that you obtain, particularly, in terms of resolution in reciprocal space, also how far out in reciprocal space you get. All of these do affect the quality of the models that you get to. This is going to be exacerbated in the cases of sample environments. So I think there's all sorts of avenues for improvement, but ultimately one of the reasons for emphasizing data analysis here is that it's very often that's the sort of the part of the process up the most.
Okay, thank you very much, Andrew. And I think we'll break now. We've got some time for a quick bio break or a quick coffee, and we'll come back in at 1/4 the hour for the next talk. So thank you again, Andrew.
The Institut L'Oeil-Langevin is the world's leading facility for research using neutrons. The ILL was the first international research center to be based in Grenoble. It was founded out of a desire for European cooperation, shared first of all by France and Germany, and then also by the United Kingdom. The ILL is a research infrastructure dedicated to serving scientists from around the world. It offers them access to the world's brightest neutron beams, a suite of state-of-the-art scientific instruments that are constantly being further developed and upgraded. the expertise of its in-house scientists, engineers, and technicians, who are all specialists in neutron science and technology. Every year, the ILL welcomes some 1,500 visiting scientists and generates around 600 scientific publications. The ILL's neutrons are used to investigate matter in a wide variety of fields: magnetism, biology, particle physics, to name but a few. The fundamental research conducted at the ILL has many applications, for example, in the health and energy sectors. More than a quarter of the research carried out is on industry-related topics. The ILL is governed by the United Kingdom, Germany, and France. 10 other European countries have signed scientific membership agreements with the Institute. These international collaborations make a significant contribution to the scientific excellence of the ILL. Once their experimental proposals have been selected, the scientists from the partner countries have privileged access, free of charge, to the Institute's facilities. Today, around 500 people from 30 different countries work at the ILL. The training of future generations of scientists is one of the Institute's top priorities. At any given time, there are over 40 PhD students working at the ILL, as well as many other student trainees. The ILL provides vital information for the development of innovative solutions to many of the major challenges facing the world today. For the past 5 decades, it has been putting its leading-edge science and technology at the service of society.
After more than 6 months of working from home for many of our employees, ESS can proudly state that the organisation has adapted to keep up the productivity. Thanks to a lot of planning, the civil construction is continuing at almost the same pace as before, even though the supply chain has been severely affected in many cases. The target building is weathertight, and the high bay crane has been installed. We have started on the signature roof, nicknamed the Sombrero. Work is ongoing on both instrument halls surrounding the target building. And installation work is ongoing in preparation for the target vessel to arrive. In the accelerator tunnel, installations of the cryo system have continued. Here we can see the connection between the accelerator tunnel and the target area, where the so-called dogleg will be. During the second quarter, the accelerator cryo plant has been commissioned at its highest capacity, which enables the cooling required for the superconducting LINAC to reach its full beam on target. In the instrument hall for the long instruments, the cave for the NMX instrument is close to finished. Work is ongoing on the cave for Bifrost, as part of the preparations that are being made for the first set of instruments that will be ready for first science in 2023. Behind the instrument halls are the laboratory buildings that were almost fully equipped when the work had to stop due to the pandemic. After adopting the workplace to the new safety requirements, the installations will be completed with no delays. Last but not least, the ESS campus, with office spaces for all ESS staff, is almost finished. The Move to Campus project has been initiated to secure the possibility to move in as planned in the first quarters of 2021. Even though we're not all in Lund every day, we do progress in building a facility with the aim of getting first science in 2023. We call it business as unusual.
Do you want to optimize your products? Do you need to analyze how your preparations behave? Why not use SANS, Small Angle Neutron Scattering? SANS lets you explore the microstructure of liquids and solids at scales ranging from 1 nanometer to 1/10 of a micron. Why is it useful to know their microstructure? Imagine you want to manufacture a shampoo with a brand new active molecule. The problem with active molecules is that they are often hydrophobic. They dilute very little in water. And shampoo is an aqueous preparation that is used beneath water. Therefore, the active molecules are encapsulated in aggregates of surfactants. But the mixture is very liquid and not very practical to use. So, a thickener is also added to the mixture. But manufacturers don't want an excessively viscous, glue-like mixture that is difficult to get out of the bottle. So, how do you best proportion each ingredient to obtain an attractive shampoo, which is stable in a wide temperature range and over time, and which is easy to rinse off? This is when things start to get really tricky. SANS measurements help you optimize your formulations. They let you observe how the molecules in your shampoo are organized. How does this work? A product sample is placed in a SANS instrument. The instrument is temperature controlled, and an injection system allows blending if necessary. A beam of neutrons is directed at the sample. The matter of the shampoo deflects some neutrons from their trajectory. A large detector records the position of these deflected neutrons. The result is curious figures, which the experts will analyze. This measurement makes it possible to determine the shapes, sizes, and spatial organization of the scatters of structures in your shampoo, ranging from 1 nanometer to 1/10 of a micron. It's even possible to detail the size and nature of the lipid layers or bilayers, the barriers that encapsulate the active molecules. SANS is a major technique that is also applied to many other systems: polymers, colloids, biological macromolecules, emulsions, pores in solids, aggregates in alloys, and even magnetic microstructures. Available in neutron centers, SANS gives you a novel perspective on the organization of microstructures.
ESS is located on the outskirts of Lund, a city with a long, rich history. It's built on the border between the city and the countryside on 75 hectares of land, and it is here the future will be formed. This is where it all starts, the iron source manufactured by INFN in Italy. Plasma is created from hydrogen gas, and the protons are separated from the electrons. These protons are then drawn into the accelerator, where they're accelerated to speeds approaching the speed of light. The 602.5 meter long accelerator is divided into a warm section, a cold section, and a section for which is set aside for future upgrades. What we see here is mostly the cryogenic system that will cool the accelerator. While the accelerator tunnel is mostly 8 meters below ground, the equipment that powers it is placed in the gallery on ground level. They are connected through stubs placed along the tunnel. When the protons hit the tungsten target wheel, the spallation occurs, and the neutrons are released from the tungsten nuclei. A moderator then collects and moderates the neutrons before they are guided towards the instruments. ESS will have 3 instrument halls surrounding the target. The largest is for the long instruments, which are up to 180 meters from the target. ESS will have 15 instruments online by 2026 and has planned for a total of 22 state-of-the-art instruments. This is where the magic takes place. Each instrument is tailor-made by scientists, for scientists, to make the most of the neutrons. As a facility focused on the users, ESS will provide the scientists with beam time at an instrument, as well as a scientist that can help these visiting researchers make the most out of every instrument. The ESS campus, where the scientists will stay during their time at ESS, includes a restaurant, auditorium, conference rooms, and office space for all ESS employees. We will move in at the beginning of 2021. ESS has more than 500 employees representing over 50 nationalities. First Science is set to take place in 2023. We will deepen our understanding of the world around us and perform research on scales never seen before. Together, we're on our way to change the world for the better.
So do we start soon, or?
Yeah, I hope so. Okay, so welcome back, everybody. I see most of you have had your break and you've joined us again. So it's my pleasure to welcome Lise Arlet from the Niels Bohr Institute in Copenhagen to talk about small angle scattering techniques and membrane proteins. So please take over, Lise.
Thank you very much. I'll share my screen first, which is here. And you all see it, or at least you see it, Shane?
Yes, yes,
Good.
I see it.
Good, thank you very much, and thank you for inviting me. And I think it's a shame that we are not either in Lund or in Grenoble. It starts to get a little bit confined here. So the title of my talk is Investigation of Membrane Proteins with Combined Small Angle X-ray and Neutron Scattering. And I'm Lise Arlet from the Niels Bohr Institute at the University of Copenhagen in Denmark. And now Michael Preuss announced this morning that he will be changing, or he has changed position. I also have to announce that as of October 1st, I will also change position to become Associate Dean for Research at the University of Copenhagen at the Faculty of Science. And this unfortunately means that I will dive a lot into politics and so on the next couple of years, and unfortunately less into neutrons and so on. But I expect to be back in some years again. So. And then I'll also say that I decided, in the light of that we already had Tamim Darwish and so on, and it's a neutron talk, I decided to change my title slightly and call it Investigation of Membrane Proteins with mainly neutron scattering. I actually don't have X-ray scattering data today, despite that it is a technique that we are using a lot in the group. So the membrane proteins, they continue to constitute one of the grand challenges in structural biology. They are important because they sit in the cell membranes and they basically take care of a lot of the signaling and a lot of nutrients transport in and out of the cells. So they are a prerequisite for higher life as we know it, and for multicell organisms as ourselves. They constitute about 30% of the proteins in the cell, and they constitute about 50% of all drug targets, so they're also important for that matter. And then they are extremely challenging to study. So out of the 170,000 protein structures in the protein data bank, there's only 3,000 of those that are membrane protein structures, and then about a little more than 1,000 of those are regarded as distinct membrane protein structures. So they are very underrepresented as compared to the 30% that they should constitute. I'll just change my pen here. So this is also why there has been numerous Nobel Prizes been going to scientists that have had breakthroughs on the membrane protein area, and some of them were Robert Lefkowitz and Brian Kobilka that got rewarded the 2012 chemistry Nobel Prize for their groundbreaking work on the GPCR receptor, which is one of the very important drug targets. And then a couple of years ago, there was another Nobel Prize to the field to Joachim Frank, Richard Henderson, and Jacques Duboucher, who had done been pushing the cryo-electron microscopy technique in order to obtain high-resolution structure determination of biomolecules in solution. And this technique is particularly used for membrane protein, and it has actually led to a strong annual increase in the number of membrane protein structures. Some of the breakthroughs is illustrated by this nice illustration here by Martin Högbom, which shows the resolution of cryo-EM before 2013, where sometimes the field would be evil to themselves and call this blobology, what they could do at this stage, whereas now they have the resolution at present, which is down to 1.8 angstroms, which was obtained in 2016, where you actually start to have atomic resolution. But cryo-EM, it still works best for compact and well-behaved folded proteins, and they still have to be relatively large. Even that limit is also going down. So there's also a requirement for complementary methods, including small angle scattering and reflectometry and NMR and so on, to obtain more information about the many more dynamic membrane protein structures. If you want to work with the membrane protein outside the cell membrane, which we often have to do if we want to do structural studies, and that be it either with crystallography or with NMR or with cryo-EM or with small angle scattering, then we have to stabilize it somehow. And there are several approaches for doing this. One of the most classical one is in detergent-based systems, as illustrated here. And then there's a range of systems, the bicell systems, peptide discs, polymer discs, and so on. And then the nanodiscs here, which were proposed some 15 years ago, and which is a system that we like to work with a lot in my group. So if you look at how good they are in the context of small angle scattering, then the detergent-based systems are, as they are when you buy them naturally, they are less good for small angle scattering because they have some intrinsic polydispersity, whereas the nanodisc systems, they are intrinsically more monodispersed, so it gives a higher resolution when you work with them in small angle scattering. So for that matter, they are better. And then if we, on the other hand, look at the ease of handling, so assuming that you also want to actually have samples at your beamline, then there's a lot higher chance of obtaining good samples with the detergent-based carrier systems, and a lower chance, and it requires more skills and know-how to prepare samples of membrane proteins in nanodiscs. So that's also a balance that has to be considered. And also I would like to give a little bit of background on the biological membrane. Sometimes we forget this when we talk about the membrane proteins on their own. But actually some of the first biomembrane models were proposed in 1935. There had been some ideas before, but Danieli and Dawson, they proposed that the membrane, it was a lipid bilayer. And then they could also see from the chemical analysis that there was some protein in the lipid bilayer. They proposed that this would lie on the outside and on the inside. A lot of research went on. And then Singer and Nicholson proposed the famous fluid mosaic model in 1972, where they had transmembrane proteins in the membrane. And as a new thing, they actually proposed that a lot of the function of the membrane proteins that took place, or a lot of the function of the cell membrane and the transport took place via these membrane proteins. Then in 2005, Don Engelman wrote a nice article where he summarized that membranes are more mosaic than fluid. And his point here was that the membrane is actually highly crowded. It's very filled with membrane proteins. When we look at these models for the membranes, then I would say the detergents, the bicells, the nanodiscs, they appear to be acceptable model systems for the membrane environment. It's not perfect, but it's also not totally wrong. But if we look at the real lipid environment in a typical cell, and it's difficult to say typical cell because there are many types of cells, but I'll just insist on calling a typical cell here. Then we look at first as a membrane protein, which is actually rather extreme. So there's a overall positive charge on the outside and a negative charge on the inside, and there's some ion concentration gradients of sodium and potassium and chloride, and also of magnesium that I'll return to later. If we look at the typical membrane resting potential, it's minus 70 millivolt over the 5 nanometer membrane. This doesn't sound like a lot with minus 70 millivolt, but if we look at the potential drop, it's actually 1.2 times 10 to the 7th volt per meter. If we compare that to a lightning, there we have a potential drop of only 10 to the 4th volt per meter. So this is just saying that it is a quite efficient insulator, this cell membrane here. Also, there's a rather extreme lateral pressure profile across the lipid membranes. This was proposed by Cantor in 1977 in a theoretical work, where he calculated that the positive pressure and the oscillations in the pressure over the membranes, or over the head groups, hydrophilic head groups, or hydrophobic tails and hydrophilic head groups, that would be varying of about 300 atmospheres over this only these 5 nanometers interval here. This is something that we still don't know how to measure and confirm experimentally, but it's hard to but there's some very convincing theoretical arguments that this should be the fact. So an extreme lateral pressure profile environment also. And then also there's a non-homogeneous lateral distribution of lipids and proteins. This figure here is from Lillemeyer and Davis from 2006, but it basically summarizes that we expect that there are more or less protein-free plasma membrane areas. Then there are non-RAF protein islands and RAF protein islands, and even the story of these RAFs or non-RAFs, that's still being debated. And then there's an emerging field of lipidomics, because it turns out that there are thousands of lipid types in the cell, which probably also matter somehow. And then also membrane proteins, and this was also indicated by Anne Imberti yesterday. They typically have post-translational modifications such as glycosylations and phosphorylations, and they may also contain large intrinsically disordered domains. A good example of this is this prolactin receptor here, which has a single alpha helical transmembrane domain, has a folded domain on the outside, and then it has a huge disordered domain on the inside. Down here, we have drawn an ensemble of different conformations just to illustrate the conformational freedom. But this point with membrane proteins with a lot of disorder on the inside, that's actually common to a lot of the membrane protein systems, and probably for some reason, but they're hard to investigate. And then also a last point I want to make is the crowdedness, which has been illustrated so nicely by Goodsell here. So it's extremely crowded. If you look at the membrane surface, it's probably about 50% membrane protein. So with all this said, I'll just say that emphasize that the nanodisk and our other membrane mimics, they are clearly very simplified model systems, but it's at least a start. But I think there's a lot of work ahead of us still. So what can we do with X-ray scattering and neutron scattering? So with X-rays, when we put a membrane protein in a lipid bilayer, either in a liposome or in a nanodisk, we obtain a contrast that looks more or less like what I've illustrated here. So we have one contrast for the protein, one for the lipid head groups, and one for the hydrophobic tails. And this basically gives rise to a relatively oscillatory scattering pattern, but that is, on the other hand, also very information rich. With the neutrons, we can of course do contrast variation. So if we don't do anything, but just take our protein and our membrane in 100% D2O, then it'll look more or less like this. We'll have a strong scattering contrast from the hydrophobic parts of the lipid tails and a less strong from the membrane protein. But then we can deuterate, and I'll talk a little about that later as well. We can deuterate the phospholipid bilayer to make it transparent or to make it invisible to the neutrons. So we can make this match out deuteration. And this means that we will only be able to see the membrane protein. And this is, of course, very interesting if you want to investigate the membrane protein structure. You could also be interested in looking more at the membrane and how it was deformed under the presence of the membrane proteins. And this can be done by going to 40% D2O and just a normal hydrogenated membrane protein. This will then be matched out and you will see the membrane with holes where you had the membrane proteins. And the strong advantage of this is that, as I've also written here, the neutrons gives us the possibility of not seeing everything at the same time. And this can be a strong advantage if you have a complex scattering pattern, that you can do this, play these tricks. The X-rays, on the other hand, they are orders of magnitude more abundant. And this means that we generally have higher resolution and we have a much better statistics, and this makes the X-rays crucial if in assembling the whole picture for more complex systems. So in those cases, we will have to combine the two techniques. So if we want to investigate membrane proteins with small angle scattering, then we have worked with two strategies in my group over the last 10 years. Strategy one has been to develop sufficiently strong modeling tools that we can interpret simultaneous SACs and SANS data from membrane proteins in nanodiscs. So we started out with working with the empty nanodiscs about 10 years ago, and where we combined SACs and SANS to obtain a more comprehensive description of the scattering data. We have continued this work over the last couple of years and refined it further and further, so that we now are able, in this Bengtsen and al. Article, are able to integrate both small angle scattering, X-ray and neutron data, and NMR data with molecular dynamics data to really obtain a much better understanding of the system. And then we have, of course, looked a lot at different membrane proteins in the nanodiscs. We started out with the bacterodopsin, which is not the most exciting protein, but it's a nice protein if you're a physicist and you want something that you can actually handle. We started out with that in 2014 and went on to the P450. The bacterodopsin work was both X-rays and neutrons. P450, we didn't have that in large amounts, so we could only study it with X-rays. This is work started by Nicolas Skar-Gislinge from 2015. And then we have worked with some other systems. At the moment, we are working on this super hard case, growth hormone receptor, where we combine X-ray and neutron scattering to investigate this very flexible membrane protein. So this is a lot of conformation of the membrane protein that I have drawn on top of each other here. And this is also a case where we need to combine NMR data and X-ray and neutron scattering data, molecular dynamic simulations, in order to understand the system. To handle all these systems, we have developed the Will It Fit software, which is documented in this article by Petersen et al. From 2013. And I would also like to point to some recent work we have done on hydrogen deuterium exchange, which is relevant when you want to look at membrane proteins in solution and you want to actually model the details, and you also have to be accurate on this point here. Strategy two that we have pursued, and which I'll focus on today, is to improve the conditions for the small angle scattering structural analysis. And we have done this by combining two approaches. The first was to use specific match-out deuterated carrier particles. So we have both worked with invisible phospholipids and with nanodiscs that we could make invisible. And then the other idea was to establish online SANS for membrane protein studies so that we can obtain ultra pure and unaggregated samples. And all this work has been taking place in close collaboration with the D Lab at ILL and D22 at ILL, and with the ANSTO Deuteration Lab in Sydney. So the requirements to make stealth nanodiscs, in order to do that, we need to make both the phospholipid bilayer and the belt invisible. The belt we could be made invisible by expressing it, match-out deuterated MSP1D1, where MSP1D1 is the name of the protein belt we are working with. And if we express that in 85% deuterated media, then we obtain 75% deuterated protein, and this implies that the MSP1D1 becomes invisible in 100% D2O. And this was of course done at the ILL D Lab. and then another thing that we did was to express match out deuterated POPC. So the idea here was that we used an E. coli strain that was PC producing, and then we systematically controlled the level of D2O and D. coli and D. glycerol in the growth medium. And then we could deuterate it 78% in the head groups and 92% in the tails. And this implied that it becomes overall invisible on all the length scales. So both the head groups and the tails then match out separately. And of course, the whole thing also matches out separately in 100% D2O. All this work was carried on via tour de force by Selma Marik, and it was carried out in very close collaboration with the ILL D-Lab with Martin Moulin and Michael Hertlein and Trevor Forsyth. So Selma Marik went on and showed that you could prepare nanodiscs of these compounds, and we could match them out at 100% D2O. This is illustrated over here. And if we look at the forward scattering, then we can also see that it also shows that how they gradually become more and more invisible as we approach 100% D2O. So the stealth discs on their own were published in 2014, and then 2 years ago, Selma Marik and Trevor Forsyth teamed up with the Henning Tidor team and exploited these with some membrane protein systems, the ABC transporter and the calcium 2+ ATPase to look at those using the stealth nanodisc technique. So it works. In parallel to this, we pursued a same principle, but with synthetic semi-deuterated detergents instead. We could see that even though we really loved the nanodisc approach, then we also lost a lot of good membrane proteins on that account, because the whole sample preparation is sometimes challenging with the nanodiscs. So we thought that if we go back and work with invisible detergents instead, then that would ease our life. So we teamed up with Tamim Darwish and his group from ANSTO, and then we prepared octyl glucoside in an invisible form and DDM in an invisible form. And again, we had to measure and calculate how we could separately match out deuterate head groups and tails. But this was indeed possible to do, and as is demonstrated on these contrast variation SANS data here, where we can show that both for the OG detergent and for the DDM detergent, as we go towards 100% D2O, then they both become invisible, and the scattering from them is not stronger than from the background. So this was all published in an article from 2018 from our group, where we applied these detergents to a range of membrane proteins. Another game changer, I would say, for us in the field has been to introduce SEC-SANS to improve the quality of the SANS data on membrane protein samples. And SEC means size exclusion chromatography, so it's basically a purification, a protein purification method that we then couple directly to the SANS sample cuvette. So we basically mix our samples, whatever, and then we run it through the size exclusion chromatography column, and which sorts it according to the different molar masses or different sizes of the particles. They are then sent into the sample cell where they are investigated by the neutrons. So this is a technique that has been around for almost 15 years with X-rays, but it was very new that Anne Martel and Lionel Pogard showed in this article by Jourdain et al. In 2016 that they could also use it in combination with small angle neutron scattering. And we then built on this work and used the same approach, and also showed that we could also use the technique in combination with much more complicated membrane proteins. And this really becomes an advantage in combination with the stealth deuterated detergents, because then we can both exchange from hydrogenated to deuterated detergents on the column, and we can put the visible membrane proteins, or membrane proteins always visible, but with the visible hydrogenated carriers into the column, but then what comes out and what is the invisible versions, because we make this exchange of the DDM over the column here. So we can actually online produce these core A here, which is membrane protein that I'll return to a little while. We can put these in, and we can actually obtain those in a form where we can measure them directly on the beamline. So this plot over here shows that there's actually a important gain of doing this online SEC SANS purification as compared to the offline SEC static SANS that we used to do. So the original approach was that one of the scientists from my group, they would prepare the samples, then they would run down to the beamline and they would start the instrument and they would start measuring. And in the other approach, we purify directly and inject it directly on the instrument. And if you compare these two plots, this should have been the same sample, but as you can see, there's more scattering from the offline SEC-produced samples, and this is a typical sign of aggregation of the sample. So this really shows us that that we obtain much better samples on this online SEC SANS approach. Also, despite that we have less good statistics, than what we have in the sample is much better. So this is an important improvement. And some of the numbers are illustrated down here, but what you can see here is that the molar mass of the SEC SANS produced samples, that is very close to the theoretical molar mass, whereas with the static SANS approach, we systematically obtain a too large molar mass, so we don't expect them to be monomeric in the form that we would like to. So, and I would also emphasize that we are one of the groups that look very much forward to the extended SANS detector that is being planned at D22, so that we only have to do this with a single SEC run in order to cover a large Q range. So the target that I'll talk about today is the core A magnesium transport system in bacteria, and I know that I have to be economic with the time, so I'll get there, I'm sure. But the core A, it's a membrane protein, and it's very present in bacterial cell where it regulates the magnesium 2 uptake, and it basically works the way that on the outside of the cells there's a surplus and there's an excess of magnesium. On the inside there's just the right amount, so a critical amount for the cells to function, but magnesium in too large amounts would become poisonous for the cells. So this is a nice big membrane protein that is relatively easy to express in larger quantities, and this is also why several groups have worked on it for many years. And there was some crystal structures of it coming out from 2006 to 2013 in the presence of magnesium, which proposed that in the presence of magnesium there was nearly symmetric closed state, as is illustrated down here. And then in 2016 there was a cryo-EM study done by Doreen Mattis and co-workers, where they showed that in the presence of magnesium, they confirmed that they had this almost closed symmetric structure, whereas there was a symmetry breaking when they added EDTAs to complex or to suck out the magnesium of the structure. So they proposed that this symmetry gating, or this symmetry breaking was the gating mechanism for the magnesium transport, so that it would be closed and symmetric, and then it would gradually open to become active and transporting. So in our study, we did SEC SANS in combination with neutron invisible membrane protein carriers, and we had the particles both in DDM and in stealth, in stealth DDM, and we had it in stealth nanodiscs down here. And I'll also emphasize here that we used what we could call second generation nanodiscs that are both circularized and they are solubility enhanced. We wrote an article about those last year. And then also in collaboration with Tamim Darwish and his group, we managed to prepare some extra invisible synthetic DPOPC, so we can really make them very, very invisible now if we want to. Then the crystal structures, or the structures that we were comparing to, so we wanted to compare to these structures that had been proposed in the literature. So we prepared samples with magnesium, and then with tiny amounts of magnesium and in the presence of EDTA to really make sure that we could suck out the magnesium like it had been done in the cryo-EM study. And the theoretical scattering predictions of the two states is illustrated here. And you can see that despite that the overall structure is very similar if you look at the low Q scattering, but if you look at the middle Q range, there's some significant differences which we should be able to pick up in an experiment. So the results are shown here, both the Core A in stealth nanodiscs and the Core A in stealth DDM with magnesium and without magnesium. There, the red and the blue, and over here with magnesium is the green and the orange. And what we note first is that and I've not shown this, that we have more or less identical signals in the nanodiscs and in DDM. So the carrier particle doesn't affect the structure in this system here. But what was puzzling much more was that we have identical signals with and without the magnesium. And this we really don't understand. Because that is, we shouldn't have that at all. So first we checked that the Core A was actually intact, and we did this by negative stain EM, and it indeed looks fine. We also did some activity assays, which I'll just rush through here, but they basically shows that it transports the magnesium as it should do. And also when we take the two crystal structures, the crystal structure and the EM structure, and compare them to the SANS data, then they actually don't fit the SANS data very well. There's some systematic discrepancies here in this range here. So what is going on? And in order to sort this out, we tried several approaches, and we have actually been working on this for quite a while. The first thing we tried to do was a normal mode analysis to find a good approximate model. This was carried out by Andreas Haahr Larsen and Ramon Creuet, which basically could show that as they allow more and more symmetry breaking and also breaking up of the secondary structure of the single monomers, then we can obtain a much better fit here. We chose a compromise here where we still have a fairly conserved secondary structure, but we have some symmetry breaking, and then we use that as a starting point for a molecular dynamics simulation of the structure that would refold the change so that we could actually fit the whole thing again. So we took that, and then we did a molecular dynamics, metadynamics simulation from this perturbed Core A structure. And then we did a lot of mathematical tricks, which I'll not dive into here, but we did an ensemble reweighing by a Bayesian maximum entropy method, which we did in close collaboration with the Lindorff-Larsen group. And finally, in the end, we could show that for both states, we obtained a dynamic example of symmetry broken states. That was the only way that we could explain our data. So what about the closed symmetric structure that has indeed been shown by crystallography? So why don't we see that? And if we actually found out that if we include a small fraction of that in our samples, then we can still fit the data. So our working model is that the closed symmetric state is also there, but most of the sample is actually in this symmetry broken state, both with and without magnesium, this is in contrast to what has been proposed in all the earlier models. So conclusion, the contrast variation SANS data suggests that the solution structure of Core A is overall similar with and without the magnesium, which was a surprise. It was also a surprise that none of the published Core A structures can fully account for the solution SANS data. And instead, a symmetry broken configuration is required to fit the data, both in the open and in the closed state. And then some NMR data, which we have not shown here, they actually indicate that some of the local protein dynamics is slightly different in the two states. And this is a collaboration with the Pintacuda lab in Lyon. And so we actually try to propose this, or are in the process of writing up a story where we try to propose this as a gating mechanism, but a much less gating mechanism that is very different from the textbook gating mechanisms where with membrane proteins, where we often have a picture of a membrane protein that is in some simple state, and then it changes its shape or changes its conformation to allow gating. And this is actually not the picture we see here. So I think that's quite exciting. And we are looking forward also to see how it'll be received by the community and how controversial that will be. So with this, I'll come to my acknowledgements. This has been a project that has been going on for several years. It turned out to be much more difficult than we first thought. There's been some very good people in my own group at Niels Bohr Institute at University of Copenhagen. Then we have also benefited a lot from the collaboration with Christian Lindorf Larsen's group at Linderstrøm Lang Center for Protein Science and Biology at KU, and with the KU Plant Science with D22 and ILL in Grenoble, and with the D-Lab at ILL in Grenoble, with the deuteration facility in Anstow, and with Stockholm University, where we got the samples from first. And then we're also grateful for Lundbeck Foundation for the funding of this. So with this, I'd like to thank you all for your attention.
Thank you very much, Lisa. We're a little over time, but maybe we'll just take time for one question. I think you might have addressed this when you talked about the sex sand, but the question is whether micellar systems are polydispersed due to variation in micelle size or protein detergent ratios.
So the micelles surrounding the membrane proteins, is that what you're referring to?
Actually, it's the question I'm passing on from someone else, so I don't know.
Okay. But if we, if you look at the detergents on their own, detergent systems on their own, they're always polydispersed when we do a classical small angle scattering studies of them. They're always polydispersed, and we strongly expect that, or there's no reason why this shouldn't be the same when we have them surrounding membrane proteins. So I would be very surprised, and there's also no reason why we should be able to separate membrane proteins, say with 150 and 160 detergents around them in a size exclusion column. They would basically come out at the same time. So there we are bound to have some smearing there. There's just too much flexibility in those systems.
Right.
Yeah.
Okay. Thank you very much, Lisa.
Thank you.
Thank you for a wonderful talk. And let's move on to the final talk for the session. And if you could stop sharing, Lisa.
Yeah, I think I can. Yeah.
I'll introduce Marek Bartowiak from the Paul Scherrer Institute, and he's going to talk to us about the latest trends in sample environment. So Marek.
Oh, I can't hear you now. Why is that? Ah, okay, it's working. Okay. Thank you very much for the introduction and for the kind invitation. You hear me? Yeah. So I'm Marek Bartowiak, head of the sample environment at Paul Scherrer Institute, and here in this meeting I'm also representing the International Society on Sample Environment. There I'm the communication officer. So I choose a catchy title: Leaks Ahead, Present and Future for Sample Environment. And of course, I would like to present a little bit what are the challenges that also lie ahead of us, and they come with the leaks like lens or leaps, as I will point out later. I would like to acknowledge people that sent presentations to me. So there's Eddie Oleg, Jürgen, Rachel, and Klaus, and of course also Yamali. So these are people from the community, from the ISSE, that helped me with out with some examples that I will come to later. So before I talk about the present and the future of sample environment, I would like to start with the past. So if we go back into the 90s, and I will pick SynQ as an example. Basically, sample environment was relatively simple. I mean, at SynQ, you see, we had a few CCRs, we had orange cryostat, furnaces, and one cryomagnet, and that seemed to be sufficient to serve the user community, which was mainly solid-state physicists. Not even 10 years later, after the reactor in Wiesel closed down, we inherited some sample environment from there. And what you see is that, of course, the number of cryostats and sample environment kits increased. We gained some new capabilities by having more magnets. and also complexity. So this is the first dilution refrigerator in combination with cryomagnets that we would have here. If we move on to what we have now, I'm here just showing the low temperature facilities or the temperature facilities. You still see the CCRs, the furnaces, the orange cryostats. There are much more orange cryostats. There are even more cryomagnets, dilution refrigerators. There are other capabilities like electric fields, high temperature sticks, and other in situ techniques. Of course, on all the other fields like soft matter or pressure, equipment has also increased and diversed. So, and that's the same for all of our facilities. So if we look at the landscape, the scientific landscape at our facilities at the moment, there's a broad and diverse user community looking at solid state phenomena, material science. There's more and more device science and also in industry applications, as we have seen in the talk by Markus Strobel yesterday. And there's also life science applications, as soft matter, as we've just seen in the previous talk, cultural heritage, fundamental physics. So I picked just a few pictures to illustrate how broad you as a community are. And of course, these are examples that you have produced and they can be looked up at the ILL Scientific News webpage. So what's the role of sample environment in all this game? Well, sample environment, the role of the sample environment team is to provide reliable sample environment equipment. And of course, to provide a variety of sample environment equipment. In addition of that, of course, we also thrive to develop new devices and push the boundaries of the parameter space. And, oops, wrong direction. And of course, we have to do this with a growing and diversing user base, with increased complexity in the scientific questions, and with a resulting complexity in the technical solutions. So if you look at the picture on the right, where I have basically a waiter serving sample environment, nowadays the job looks a bit more like this. So we are constantly juggling between equipment, and the question is, how do we free our hands in such a juggling job in order to do development of novel devices and push the boundaries? I would say the solution is that we achieve this by automatization, standardization, in some respect also by optimization, and of course by collaboration. I will now go through all these 4 points and illustrate them with some examples that have been provided to me. So automation, if we talk about automation, of course, it's clear that automation improves reproducibility of conditions and processes. It reduces the risks of making a mistake if the process is once set up. It also lessens the requirements on the user skills. So you don't have to be an expert in running a specific device in order to execute an experiment. And of course, it frees time for us, for the operating teams, sample environment teams, and it's easy to scale these things. This comes not for free. Setups become more complex. That means the way to maintain them and to provide them to you requires different skills in sectors like mechatronics and programming. And of course, it requires the proper infrastructure in order to do automation in a way that it's actually meaningful. So as an example, I would like to show the demand on ultra-low temperature sample environment. As you can see here, there's a graph on the number of ULT experiments per year at ISIS in Rutherford. And you see the demand is ever growing. So you have a growing demand, which leads basically to a build up in devices, which leads to a growing demand. And to overcome or to be able to fulfill this cycle, what you have to do is to automize, and you can nowadays buy automized gas handling systems for dilution refrigerators. But of course, the commercial ones are not optimized for a facility. And I would like to show here the new gas handling system that has been developed at the ILL. It's fully automated. You can change temperatures between 40 and millikelvin and room temperature continuously. It's compatible to all cryostats at ILL, so it is actually made for the infrastructure at ILL, and it has some conveniency like automatic data storage and so on. In the bottom, you see a temperature curve over 3 days, I believe, where temperatures vary continuously between room temperature and the base temperature of the system. These systems have now been in use for at least 1 cycle, maybe even 2. And of course, being so successful, it's then easy to scale this to provide even more dilution experiments or ULT experiments. Another example from the ILL is the new absorption troughs for Figaro. Here, the system has been scaled up to provide room for 8 to 12 samples. It's automized in a sense that it has gas circulation, surface tension monitoring, temperature control. You can check up on the position of the interface, and then there's some commodities like no condensation on neutron windows and a user-friendly touchscreen interface. If we come to optimization, which is sort of another key aspect in order to prepare ourselves for the future, of course, optimization is something that should come after the initial R&D that you do in order to increase the performance in a particular area. So whatever you want to optimize, neutron background measurement time. The drawback is that equipment becomes more purpose specific. And of course, you need to know the requirements for this optimization. So you need to know what you optimize for, and it takes time of your initial development time. But of course, the payback that you get is that once you optimize, that's at least for that purpose, it's assured that this is the best possible outcome. So you can basically, leave that development saying this is the best we can do with this method, with this optimization. So you are free to do something else with your time. An example here I want to show from SIGN 2020, which was a program where Sample Environment wanted to use or to promote efficient techniques for efficient use of neutron beam time. Here, what is shown here is an optimization process of a high temperature furnace, and the cool down of a high temperature furnace is fast cool down. What you can see in the graph here are different cool down curves, either with just leaving the system alone without heating, or by introducing exchange gas into the vacuum chamber at specific times and in specific ways. And by doing this optimization process, the cool down times from 1000 degrees Celsius to 80 degrees Celsius could be reduced from 4.5 hours to 45 minutes. So this is a substantial saving in beam time. Yeah. Another high temperature example that I would like to show is what you see in the picture on the right is a halogen lamp furnace that was developed at the MLZ. And based on this design, they started to also now work on a laser furnace. Together with us at PSI, we started to revise this design. We optimized it for ease of use, of course. We symmetrized the setup. We tried to get to simpler parts. And of course, the main driver was there to also include the capability of gas loading, which would allow you to heat samples in a gaseous atmosphere, or use a gas flow in order to cool the sample quickly. From seen in 2020, another example for optimization is the look for new pressure materials or pressure cell materials for inelastic scattering. There we together with theoretical support from the University of Zaragoza and did some studies on several materials, and it is apparent that TUF6, which is a titanium alloy, seems to be a very good candidate to make inelastic cells. You can see in the spectra, that's the one on the right, in the middle on the right, that's TUF6, that there's basically a homogeneous background, more or less. So you can expect that in the upcoming years there might be a new generation of clump cells for inelastic scattering. Standardization is another arrow in the queue that we have. Well, standardization is clear, it decreases ambiguity. You know what you can expect of a standard. It improves and actually guarantees quality. It makes implementations easier. It becomes or may become a cost-saving factor or a factor of having parts available. And it doesn't hinder development because it actually frees resources for R&D. And to illustrate this, I have this picture of a Lego submarine. So Lego, these stones are standardized, but what you build out of them is only limited by your imagination. So you can make a submarine out of it. For sample environment, as an example of standardization, I would like to use SECOP. SECOP is a communication protocol that's supposed to be inclusive, simple, self-describing. Inclusive means that it's not bound to a specific concept of instrument control or experiment control system, and it should be integrated easily into your workflow. It's simple in the sense that it can be implemented by non-experts. So it's really reaching out to the user community to use this, to implement it. It can be implemented on limited hardware, but it is then used to describe complex sample environment. The unique feature here is the self-describing aspect. So we are not only transporting parameters, but we also transport metadata, which can then be used by the ECS to decide what kind of device we have and how to react to it. This is a collaboration that was strongly pushed by CENA 2020, the ESS, HZB, and MLZ and PSI. So how does SECOP work? Here I have shown an example on the left. You see a standard instrument control software, which may talk directly to the sample environment hardware. And what we do is we take a scissor, we cut the ECS part. We leave a part which is controlling the instrument, but in order to talk to sample environment, we introduce a SECOP adapter, which has to be programmed only once, and then provides a standard interface down to the sample environment controller, or called the SEC node, which is basically doing the abstraction of the hardware. So you have the sample environment hardware at the bottom, and talking to a program which does the abstraction. So going over from current values and voltage values to something which is like a magnetic field, and this is then communicated to the ECS. Because the ECS, the instrument control or the experiment control software, doesn't have to change once it's adapted, this really lowers integration efforts and makes it possible to easily bring devices from one facility to another. This is in particular interesting for users that move between facilities or that use similar setups at different facilities. The standard is now out, it's published on GitHub. So this, you can have a look at GitHub, or even better, you have a look at the paper published in the Journal of Neutron Research, which describes this standard and gives an introduction on how to set it up by yourself. Currently, there are implementation at the MLSAT and PSI, and ESS is also working on it, and I presume ILL will implement this very soon. I show you here a picture of the first NICOS instrument at PSI. It's a PPMS, and we use NICOS to control or to program this TriStat, this PPMS, and as you can see in the middle, you have these FRAPI headers. This is basically the sample environment control software talking then SECOP to the NICOS interface here. So it is running and working. The last aspect that I would like to talk about is collaboration. And here I now finally would like to introduce the ISSE, the International Society on Sample Environment. We are a society of sample and environment groups or enthusiasts worldwide. The idea behind, or our philosophy, is that we would like to strengthen our position or the position of sample environment at the scattering facilities. We can act as an international representation to political forums or scientific forums, and we would like to promote communication and information exchange between our members, and of course train young technicians and engineers or researchers. We run a webpage, sampleenvironment.org. Over there, we inform about workshops, forums, and it's the access point for our members to interact with each other. At the moment, the ISSE has 20 institutional members, and we have members from neutron facilities worldwide, as well as X-ray facilities, so the synchrotrons and free electron lasers are in there. We also have 14 corporate members. These are companies that provide sample environment equipment or are just interested or auxiliary. And we have more than 200 personnel members. The activities that we host are a biannual international workshop, which is an international workshop, and we just had the 10th 2 years ago. In between the workshops, we now have biannual training schools, and of course on the website we run forums on several sample environment topics, and provide an archive for presentations that have been given at the workshop or the training school. In addition to this, the ISSE coordinates projects via committee. One I introduced already, which was SECOP. Another one is a helium management or helium stewardship system to promote efficient use of helium and helium reliquefaction. And there are 2 new committees that will be set up soon, one on soft matter and one on a sample environment database. ISSE members are actively participating in leagues. Now I'm coming back to my title. So we are participating in LEAPS, and which is with the League of photon sources, and of course we are participating in LENS, which is the League for the neutron sources. So let me just finish by talking a little bit about our role in LENS, or how I see it. Well, sample environment is grouped in work group 3, which as Helmut Schober has explained yesterday already, the approach here is to use a science-driven approach, and that means we adopt a more holistic approach to the development of new techniques. So we will look at the entire chain from the source over the guide, sample environment, sample preparation like deuteration, for example, then of course the detectors, and in the end even the analysis. So there are 4 priority actions which are promoted. One is electronic spectroscopy, and in the past, one would have said that here we are talking about just a magnet, but that would be just the sample environment part. I think if you look at the whole chain, we have to really think about not only the magnet, but also on the instrument and maybe even the neutron source that can cater a system like that to provide the science that is sort of put forward in this PA. If you think, or if as a consequence of this approach, we require an involvement of all facilities, which is beyond the boundaries of an individual facility. And that brings me to my last slide, where I first would like to summarize and then come back to the challenge that sort of result of this lens activities that I can see. I hope I convinced you that sample environment is an integral part of the scientific effort at the facilities, that collaboration, optimization, standardization, automation are key to keep the growing demand and complexity manageable, and the free resources for new developments and novel ideas. And of course, now here I'm calling on you as the user base, which is basically our main source and partner for R&D work on novel devices. The challenges that will lie ahead in the future that I can see is the question on how we collaborate beyond the bounds of a facility, and which means how do you ensure the return of investment. So we need to find a way to make the sharing of novel development interesting to the developer. With this, I would like to conclude, and thank you very much for your attention.
Thank you, Marek. Thank you for that very interesting talk. I think the questions I'd like to start with relate to this SecOp development that you were discussing.
Yeah.
This development of the interface that I guess it allows you to go beyond the local facility. It seems that you've got strong engagement from facility representatives, but what about in other places, universities and so on? Is the collaboration include input from other more user-oriented teams?
Yes and no. For the definition of the standard, that's something that was done and strongly pushed within the SIGN 2020 program. And there was basically no input from universities. We have one adapter now who would like to use it from Prague. So there they are running a solid state physics lab, and they would like to use this to control their offline experiments. I can say that at our facility, I'm using it for offline experiments, and I can see a big benefit for me is that, or for our facility, is that we can develop stuff offline and then relatively easy transfer it into a productive system at the user facility. And my hope is, of course, that we can sort of roll this out to university partners so they can implement or use this standard to bring their equipment to our facilities, because there's a lot of knowledge and R&D work that we can benefit of as the facilities from the user base, from universities.
Yes, I think so. I could imagine that there's a great potential out there in the broader community to build a much stronger program of specialized equipment that could be moved. But when we talk about moving equipment around, very often we have to deal with the fact that things get broken in transport.
Sure.
Is that an issue that you're looking into?
Yeah, I think this is in a way a part of the challenge that we have to face. I mean, we really have to think of how do we value correctly the involvement of people that bring in equipment. I mean, if we talk about also sharing equipment between facilities, the question of what happens if it breaks during the transport is a question that only arises if we haven't really talked about how we pay back that loaning or that transport of the equipment. So we have to figure out how to make this visible for the facility. I mean, national facilities, they get national budget, so why should they give equipment out to another facility? And the only sensible reason to do this is to be visible as well. So if for example, an experiment is happening at ILL and requires, let's say, equipment from the MLZ, then in principle, we have to talk about how to share the scientific results. So how that MLZ would then also account for this publication on their side. So I think we have to discuss this, and I wanted to use this opportunity to plant that question.
Yeah. Yes. So perhaps just one more question here in relation to the networks that you formed. This organization, ISSE, but also you mentioned LENS and LEAPS and so forth. Do you have links with the instrument engineers? And is there some sort of dialogue there that can be of mutual benefit for the two societies?
Yes, we are in contact with them. Actually, the plan was already this year to have a workshop side by side with a session which is a shared session between the two communities, and because of the COVID situation, of course, that was postponed, but we are actually hoping to do this next year, hopefully. So yes, we are starting the dialogue, and both sides are open to this. So I think it's a starting point, and I think we should work on that a bit more.
Okay, thank you very much. And thank you for your presentation, and thanks to all the speakers for the excellent talks. It's rather difficult to run these meetings in a virtual way, but I think we've been really treated today. So thank you very much, and goodbye for today.